In this video, we're going to review what an inverse function is, and we're also going to look at how to take derivatives of inverse functions. And it's just going to be a formula that you're probably going to have to memorize. So first of all, there's a couple things that you should have already learned about inverse functions. The first one is that they are reflections across this line y equals x. So if y equals x, then x equals y. And our x and y's will be flipped. And that's, let's see, right here. Domains of f are going to be range values of the inverse. So it's just the x values are your new y values, and the old y values are now your new x values. If we take an inverse function and plug it into the original, it should simplify to just x. The same way with if we take the original and plug it into the inverse, we should get just x. So kind of like ln and e, we've seen those before. If I take the natural log of e to the x, they have to just equal x because they're inverse functions. Anyway, so when we see this f to the negative first, we read that as f inverse, so don't think it means to the negative first power. We already talked about it being the reflection. In order to have an inverse function, it does have to pass the horizontal line test. And so that's just the opposite of that vertical line test. That means as long as it only crosses a horizontal line once, then it has an inverse. And then very briefly, we are going to actually find inverse functions just so that we understand why we have to use a formula sometimes. So what we're going to do is we're going to get x by itself, then we're going to switch x and y, and we do have to make sure that we give our new domain. Okay, and then all this says is that these ordered pairs will be flip-flopped from an original function and its inverse. So our first example says we actually have to find the inverse, and we're going to state our domain and range of our new function. So the original function, the domain, just remember we cannot take a square root of a negative number. So our domain is going to be that x could be anything greater than or equal to 3 because we can't have 0 in there. If we plug 3 in, we get 0. So our range is going to be anything greater than or equal to 0. You can choose some other values, plug in 4, and you get 1. So you can kind of see what those domains and ranges will be. And that's for our original function. Then to actually find the inverse, we first have to isolate the value of x. So first I'm going to square both sides so that we get y squared equals x minus 3. Then I'm going to add 3. And then I get that y squared plus 3 equals x. And then to turn it into the inverse, I just switch these two. So it's going to be y equals x squared plus 3. So this is the inverse function from what I started with. And then my new domain is my original range. So this is the new domain. And so I can say my new domain is going to be x to be anything greater than or equal to 0. And then my new range is going to be my old domain. So y can be anything greater than or equal to 3. Okay? So the only reason we did that is just to show you how to find it. We first had to isolate this x. And that's not always possible. And since that's not always possible, we have a formula for what we do if we can't do it. So we're going to see questions that are going to ask us to find the inverse function and then take its derivative. If we can't find this inverse function, then obviously we can't take the derivative. So this formula allows us to find the value if without actually being able to find the inverse. And so, you know, nothing about this is mathematical, but the way I remember this is since we're dealing with inverse functions, I put everything on the bottom. And then what I do is I just take each of these inverse symbols, the inverse and the derivative, and I flip them because when I hear that word inverse, it makes me think opposite. So you can see the derivative is actually on the outside now, and the inverse is on the inside. And so now we have this composite function, and we're going to go through how to use this, but we always start on the inside of a composite function. And we are going to use the fact that ordered pairs are opposites of their original function. So my new domains are my old ranges, and my new ranges are my old domains. Okay, so in this example, we have to use this formula. And the reason is that the question says to find the inverse function and then take the derivative. Well, remember to find the inverse, I have to isolate x. And in this equation, I cannot get x by itself because this guy's to the third and this guy's to the first. So I can't do it. If I could, I would find a new function for the inverse, and then I would go through and I would take the derivative of whatever I got. Again, I can't. So when I use this function, we are going to start on the inside. And the question wants me to plug in 5. So if I'm finding the inverse of 5, I just plug 5 in here. And this is where I need to start. I need to find the inverse of 5. I need to know what that's equal to. Well, remember in function notation, this is x and this is y. And because this uses the inverse function, I can look at the original, and I know that these values are going to be swapped. So I know that I'm really looking for some x value if my y value is 5. And if you read this, this says set the function equal to 5. And we can use our graphing calculator here to set this function equal to 5. And when we do that, we'll be able to just basically plug and chug into this formula. So if you use your graphing calculator, you should get x equals 2. That means that 2, 5 is an ordered pair on my original, so 5, 2 must be the ordered pair on the inverse. And so I'm going to take this piece out, and I'm going to replace it with 2. So I'm just going to copy this down here. So I have 1 over f prime of now 2. And all I'm doing is plugging and chugging into this formula. And this I can solve. And the reason I can solve this is because this says now take the derivative of that original function. And we have the original function. So I can find f prime. F prime in this case would be 3 halves, 3 halves x squared plus 1. And this is now plug 2 into this derivative. So f prime of 2 equals 3 halves times 2 squared plus 1. Or 3 halves times 4, plus 1, which is going to be 6 plus 1, or 7. So I know that f prime of 2 is equivalent to 7. So all I do is plug that into this formula. So 1 over 7 is my final answer. Okay. We're going to do, I think, one more example on this. And this one now says find f inverse derivative of 2. So if I could, I'm going to find the inverse function. I'm going to then take its derivative and plug in 2. But if we look at this, I can't find the inverse because I can't isolate the x. So I must use this formula. Okay? So, again, here's how I remember this. The inverse derivative of 2, of 2. Remember, we're going to flip the whole thing. And then I'm going to take these two here and flip them. So I'm going to take the derivative first, and then I'm going to plug in the inverse of 2. And remember, this is where we're starting. So f inverse of 2 is what I'm looking for, which means I can use the original function, and again, those x's and y's are just switched. I'm looking for this x value. So I need to set the function equal to 2. I need to set this equal to 2. And I see if you use your graphing calculator, we'll get that x equals 0. So what that means is that if f of 0 equals 2, then f inverse of 2 must equal 0. And I can use this to replace f inverse of 2 with 0. So I really have 1 over f prime of 0. And now this says take the derivative and plug in 0. Well, I can take the derivative of f because I know what f is. So f prime of 0, how about f prime of x, is equal to 15x squared plus 5. And now I need to find f prime of 0. So 15 times 0 squared plus 5 is just equal to 5. So since I know that f prime of 0 equals 5, I can plug in 5 right here. And I see that this entire value of this guy here is equal to 1/5. And the next section in the notes, we're going to save for the next video.